Hello dear student, myself Dr. Surekha Jaiswal, Head Department of Physics, Moreshwar College, Bhokardan, District, Jalna. Today we will see Electrodynamics, paper code number 302, paper number 16, semester 5. Now see, today's topics are Maxwell displacement current, Maxwell equation in matter, Maxwell equation in differential form, and derivation of Maxwell equation. Now Maxwell displacement current. Displacement of current is basic concept that is essential for the existence of electromagnetic waves in vacuum. Best example of displacement current is capacitor. Now see in figure, consider a capacitor and wire, and if we apply as here AC supply, it is applied to this device, the current flowing in the conductor is because of electron, flow of electron here. So whereas there is no flow of electron between the capacitor, but AC supply can pass through this capacitor easily just because of displacement of current. In the presence of electric field, polar molecules of dielectric turn to and fro, providing the movement of force of charge. Such displacement of charges causes current. Maxwell called this current as displacement current. The rate of change of displacement current vector d with time is called as displacement current. It is different from conduction current, which takes place due to actual flow of charge. Further, according to Maxwell, the conduction current and displacement current are indistinguishable from each other as they produce identical effects such as heating effect in medium and production of magnetic field around. The electric charge displacement producing magnetic field and varying magnetic field inducing an EMF is a direct consequence of assumption that a displacement current can flow where no conduction current is possible. The displacement current leads conduction current by 90 degrees. According to Maxwell, the conduction and displacement current exists in all material conductors or dielectric. Now, voltage across a resistor causes continuous flow of conduction current. In capacitor, there is current only while voltage is changing, and it may be called as displacement current. In the capacitor, the current does not flow through the capacitor, but it looks as if since as much current flow out of one plate as flows into the opposite one. It is apparent current which is necessary to bridge the gap where there is no conduction current. For a capacitor of capacitance C connected to a AC voltage source V, we can write expression for current I equal to dq by dt, where I is a current, Q is charge. Now current is here given by dq by dt equal to C into dV by dt as Q equal to C into V. Q is a charge. The capacitance C is given by C equal to epsilon A upon D, where epsilon is permittivity of medium between the plates. A is area of the plate and D is separation between the plates. With value of C, the current I can be written as I equal to epsilon A upon D into dV by dt. But we know that E equal to V upon D, and therefore putting this value of I equal to epsilon A into d by dt, or I upon A equal to J equal to epsilon d by dt. We know that electric displacement D is given by D equal to epsilon into E, and therefore the expression for the displacement current density J suffix D, Jd equal to dd of dt. In general, vector D may vary in space, therefore Jd equal to delta d by delta t. Here Jd does not represent a current which directly passes through a capacitor. It is only apparent current representing the rate at which flow of charge takes place from electrode to electrode in the external circuit. Now see Maxwell equation in matter. Now there are four fundamental equations in electrodynamics specifying divergence and curl of electric and magnetic field, known as Maxwell equation. Electromagnetic phenomenon in all types of stationary media such as linear, non-linear, isotopic, non-isotopic and homogeneous, non-homogeneous can be explained on the basis of Maxwell equation. Now Maxwell equation summarize all known laws of electromagnetics. The integral form of Maxwell equation decides under laying physical laws. On the other hand, differential form are useful in solving problems. These four Maxwell equations in differential form are written as: first, that is a del dot D equal to rho F, where this law is a Gauss law stating that the total electric flux density D through a surface enclosing the volume is equal to the charge in the volume. D is electric field displacement measured in coulomb per meter square, and rho F is free charge density measured in coulomb per meter cube in SI system. The second equation is del dot B equal to 0. This is Gauss law for magnetic fields, and isolated magnetic charge does not exist. The net magnetic flux in a closed surface is 0. We know that B is a magnetic induction measured in Weber per meter square. We know the unit of magnetic induction B, that is Weber per meter square. And the third equation is del cross E equal to minus delta by delta B by delta T. This is Faraday's law stating that an EMF over a closed path is equal to the time derivative of magnetic flux density through the surface bounded by the path. E is the electric field intensity and it is measured in volt per meter. The fourth Maxwell equation is del cross H equal to J F plus delta D by delta T. This is Ampere's circular law modified by Maxwell for magnetic field accompanying an electric current. Magnetomotive force around the closed path is equal to the sum of conduction current and displacement current through the surface bounded by the path. H is magnetic intensity and it is measured in ampere per meter. Jf is current density and suffix F stands for free charge. Now see Maxwell equation in differential form. This table shows the statement of Maxwell 4 equation in differential form. Now Maxwell first equation, that is del dot D equal to rho. This equation is obtained by the application of Gauss theorem to electrostatic. In this equation, D equal to epsilon into E is electric displacement in Coulomb per meter square. Now second equation, that is del dot V bar equal to 0. This equation is obtained by the application of Gauss theorem to magnetic field, where B is magnetic induction in Weber per meter square. Next equation, that is del cross E equal to minus delta B by delta T. This equation is obtained by application of Faraday's and Lenz's law for electromagnetic induction. E is the electric intensity and is measured in volt per meter. Now next equation, that is del cross H equal to J plus delta D by delta T. This equation is obtained by Maxwell modification of the Ampere's law in circular form for magnetic field associated an electric current. H bar is the magnetic field intensity and it is given in ampere per meter, where J is current density and its unit is ampere per meter square. Now this table is summarized here, the Maxwell 4 equation. First equation is del dot D equal to rho, second del dot B equal to 0, and third is del cross E equal to delta V by delta T, and fourth equation is del cross H equal to J plus delta D by delta T. First equation, that is del dot D equal to rho, is obtained from the Gauss theorem of electrostatic, and del dot B equal to 0, this is obtained from Gauss theorem in magnetic field, and del cross E equal to delta by delta T. This equation is obtained by Faraday's law and Lenz's law of electromagnetic induction. And fourth equation, that is del cross H equal to J plus delta D by delta T. This is obtained by Maxwell modification of the Ampere's law in circular form for magnetic field associated in electric current. Now, derivation of Maxwell equations. First, del dot D equal to rho F. Now, consider a volume V bounded by a surface S in a dielectric medium. Now, according to Gauss' law, the total electric flux through the surface S is equal to the total charge enclosed by the surface. In dielectric medium, there exists free charges and polarization charges. The total charge density rho is given by the sum of free charge density rho F and polarization charge density rho B. Hence, the Gauss law for the present case expressed as integral over surface S E into dA equal to integral over volume V del dot E d tau equal to 1 upon epsilon 0 integral over volume V rho d tau. But rho equal to what? Rho F plus rho B. And the polarization charge density is given by rho B equal to minus del dot P, where P is the polarization. Now, rho equal to rho F minus del dot P. Now, putting the value of here rho B. So, we get rho equal to rho F plus minus del dot P. Using this Gauss law becomes integral over V del dot E d tau equal to 1 upon epsilon 0 integral over V rho F minus del dot P d tau. Now, integral over V rho epsilon 0 into del dot E d tau equal to integral over V rho F d tau minus integral over V del dot P into d tau. So, integral over volume V epsilon 0 del dot E into d tau plus integral over volume V del dot P into d tau equal to integral over volume V rho F d tau. Now, integral over volume V del dot epsilon 0 E plus P d tau, equating these two integral here, equal to integral over V rho F d tau. The quantity rho epsilon 0 E plus P is electric displacement vector D, and this is the above equation becomes integral over volume V del dot D d tau equal to integral over V rho F d tau or del dot D equal to rho F. These modified forms of Gauss law and state that the net outward flux of electric displacement vector through the surface enclosing a volume is equal to the net charge contained in the volume. When the field is isotropic, the three vectors D, E and P are in the same directions, and for small field D is proportional to E, and here D equal to epsilon into E, where epsilon is called dielectric constant of medium. Now second equation, that is del dot B equal to 0. According to Wyatt and Savart law, the magnetic field B at point r equal to xyz in terms of an integral over current distribution J x dash y dash z dash as shown in figure here. According to Wyatt and Savart law, Br equal to mu 0 upon 4 pi integral J r dash into r cap upon r square into d tau dash. Now in the above expression, B is a function of field point x, y, z. J is a function of the source point x dash, y dash and z dash, and R is a separation vector seen in figure, and d tau is a small volume seen in figure. D tau is a small volume element considered at source point x dash, y dash and z dash. From this point x, y, z, here the separation distance, that is a r. The integration is to be carried out with respect to the source point. The divergence and the curl are to be taken with respect to field point. Now applying divergence to the above equation, we get now del dot B equal to mu 0 upon 4 pi integral del dot J cross r cap upon r square into d tau. Now we know that del 1 upon r equal to minus 1 upon r square. Now putting this value in above equation, we get del dot B equal to minus mu 0 upon 4 pi integral of del dot J cross del 1 upon r into d tau. So using this vector identity, del dot A cross B equal to B dot del cross A minus A dot del cross B. Using this identity, equation becomes del dot B equal to now minus mu 0 upon 4 pi integral of del 1 upon r into del cross J minus J dot del cross del 1 upon r into d tau. Using this identity, this equation becomes, we can write like this. So here del cross J equal to 0 because J is a function of source point variable and it does not depend upon the field point variables x, y, z. So as the curl of gradient of scalar quantity is always 0, we have for the second term in the above equation, that is del cross del 1 upon r. See here this quantity del cross del 1 upon r is also equal to 0. So we get del dot B equal to 0. And the above equation suggests that the magnetic field lines are always continuous. There are no free or isolated magnetic charges present in the magnetic field. The net outer flux through any closed surface is 0, and the number of magnetic lines of force entering any arbitrary closed surface is exactly the same as leaving it. Now, equation third, that is del cross E equal to minus delta B by delta T. An EMF is the work done in carrying unit positive charge completely around a loop and is given by here induced EMF equal to closed integral of E into dl, where E is electric field intensity and dl is line element. According to Faraday's law of electromagnetic induction, the induced EMF due to change in magnetic flux linked with a coil is given by, according to Faraday's law of electromagnetic, induced EMF equal to minus d phi v by dt. The magnetic flux is given by phi v equal to closed integral of B dot dA, and therefore the expression for EMF becomes induced EMF equal to closed integral of delta B by delta T into dA. And equating above equation for EMF, we can write closed integral of E into dl equal to minus integral of delta V by delta T into dA. Using Stokes' law, the line integral on LHS can be converted into surface integral. So we can write closed integral over surface S del cross E dot dA equal to minus integral of delta V by delta T into dA. This equation be true for any arbitrary surface, and hence the two vectors in the integral must be equal, and hence del cross E equal to minus delta V by delta T. Now, fourth Maxwell equation, that is using here that del cross H equal to J F plus delta D by delta T. This equation is using the Ampere-Circuital law. So this equation is obtained by correcting Ampere-Circuital law. According to Ampere's law, the work done in carrying a unit magnetic pole once around a closed arbitrary path linked with the current is expressed as closed integral over surface S H into dl equal to I. The conduction current is given by I equal to closed integral over surface H J F into dA, where the integral is taken over the surface through which the charge flow corresponding to current I takes place. By changing line integral to surface integral, we get modified the Ampere's law as closed integral over surface S del cross H dot dA equal to closed integral over surface S J F dA As the integral are equal, the integrand should be equal, and we write del cross H equal to JF. The above relation is true only for steady current, and for changing current it should be modified for instant. Let us take the divergence of the above equation. We can write divergence of curl of a vector is always 0, and therefore we can write del dot del cross H equal to del dot JF equal to 0. This result contradicts with the equation of continuity. Del dot JF equal to minus delta rho by delta T. According to Maxwell, this difficulty arises due to incomplete definition of current density, and the displacement current density JD should be taken into consideration along with conduction current density JF, and thus the Ampere's law would be modified as del cross H equal to JF plus JD. Taking the divergence of the above equation, we write as del dot del cross H equal to del dot J plus del dot JD equal to 0. Therefore, del dot JD equal to minus del dot JF equal to delta rho by delta T. But the Maxwell first law reads as rho equal to del dot D. Now putting the value for the charge density, we get del dot JD equal to delta D by delta T, del dot D equal to del dot delta D by delta T, del dot D equal to delta D by delta T, and this is the value of JD for the modified Ampere's law becomes del cross H equal to JF plus delta D by delta T, and this proves the Maxwell fourth equation, and this is known as modified Ampere circular law and is valid for steady state and time varying field. This equation interprets that the magnetomotive force around a closed path equal to the conduction current plus displacement current through any surface bounded by the path. Thank you.